Okay, it's working. So the question is, are you guys on the second ice table?
Yeah.
If you're on the second ice table, you want to reset the water equilibrium. You don't want to put in 10 to the minus 7 and 10 to the minus 7. If you put in 10 to the minus 7, 10 to the minus 7, you're just making the math harder for you. And so the easiest thing is to just reset both of them to 0. And your life will be a lot easier. Let me just show you. In fact, I wouldn't even have 2 lines. The only reason I have 2 lines there is we just assume water hasn't done anything yet. And so you just say, okay, even though that's not true, you know, but it's no problem because we can approach equilibrium from any direction. It's like the water flow thing. And so I say that there's 0 molar hydroxide for sure, but here I don't say there's 0 molar hydronium because we're doing this stepwise. And there's going to be hydronium present, and how much hydronium is going to be present? Yeah, right. And so initially, this is, I don't write 2 lines, I just write 1 line. Like that, that's my initial. This is initial, where did this come from? This came from step 1.
Also, at the beginning, we don't have to do 0, 0. We can just jump to that.
Right.
Okay.
You could do 0, 0 if you don't see it right off, you know. But the reason I did it, I just did it the first time, but I don't do it anymore because we'll just save time not having to write it. But if you want to, it's fine. You could write 0, 0 from water. We're assuming that nothing's reacted. In fact, we just reset the equilibrium to left. Because it's gonna be new equilibrium conditions. Those numbers aren't valid anymore. 10 to the minus 7 molar and 10 to the minus 7 molar, you gotta throw them out because those aren't gonna work anymore. Because when Le Chatelaise perturbs it, we're gonna get a new set of equilibrium concentrations. But there are 2 methods. There's the reset method and the Le Chatelaise perturbation that we did in the last chapter, chapter 15. Le Chatelaise perturbation is a lot more work. So tell me when you get the answer, and then we'll go from there. Also, tell me if you're getting stuck on something. Let me know what you're getting stuck on.
I know I got 6 point. Yeah.
So you have an answer now? What'd you get?
5.99.
5.99? And so you got 5.99. Give me one more digit.
5.
5?
Wait, no, 6.
I'm sorry?
6.
6? You don't round it.
Oh, okay, it's 5.
5.995 times 10 to the...
No, that's what I got when I calculate the
That
amount.
was a pH.
Oh, that was a pH?
Yeah.
Ooh, pH, unfortunately, that's off. Yeah.
For pH, I got
7 point what?
7.022.
7.022? No, that's wrong too. 7.022 would be basic. Anybody else? Where are you getting stuck? Because obviously, if you're getting stuck someplace, let me know. Let me try to. The calculation problem? Okay. Maybe you don't have the. Do you guys have the quadratic solver?
Yeah.
You have the quadratic solver? You have the quadratic solver. Shouldn't get stuck. All right. Basically, this calculation is just a repeat of the previous calculation. You just change the number. Setup is exactly the same. Simplifying assumption will not work though. Did you try the simplifying assumption? And so, well, let me, because I can't take any more time. I already spent too much, but you know, ideally, what you want to do is you want to practice this calculation so that it just takes you a few minutes. You know, it really shouldn't take you, but what it means is just getting familiar with it, because all the calculations are going to be the same. So step 1 is the biggest K, so we'll call this step 1. So this is the HCl, H2O liquid. This is a one-way reaction. So with one-way reactions, I don't normally draw the 2 arrows here. This is going to give us hydronium plus chloride. Now, this is K. A is very large. And, you have to memorize this. Memorize for strong acids. And bases. Bases are different. We'll talk about bases next. Okay, so here, water is a liquid, so we'll just omit that from the table. But here we're going to have 1.0 times 10 to the minus 8 molar, 0, and 0 molar. And change is complete, so at equilibrium it's going to be 0 molar, 1.0 times 10 to the minus 8 molar, 1.0 times 10 to the minus 8 molar. So did everybody get this? The step 1? Okay, that's good. Let's move on to step 2. What we're going to do in step 2 is this. Step 2, we're going to carry the hydronium. The hydronium is going to be transported to step 2, but the chloride stays. And so we're going to have this much chloride because that doesn't participate in the next equilibrium. So that's not a common species. But a common species here is the hydronium because the H2O liquid and H2O liquid will have hydronium present. As well as hydroxide. And so what I do here is water is a liquid. I just assume it's 0, so the only thing starting here would be from step 1, 1.0 times 10 to the minus 8 molar, and nothing from step 2. In step 2, I'm going to generate the hydronium and hydroxide. Let me show you an error the book makes. This is an error the book makes frequently in the solutions manual. In the solutions manual, watch out. They do this. Hey, wait, I know what KW is. KW is 1.0 times 10 minus 14, which generates 1.0 times 10 minus 7 molar hydronium and 1.0 times 10 minus 7 molar hydroxide. So the book does this more than once, I think, in the solutions guide. They just said, oh, you know, we know water is going to generate 1.0 times 10 minus 7 molar hydronium and 1.0 times 10 minus 7 molar hydroxide. But that's not possible. That's not possible. Why? And so, oh, then this comes out easy. The book is going to come out with 1.1 times 10 to the minus 7 molar and 1.0 times 10 to the minus 7 molar. This is not possible. Why?
It's not the same concentration and stuff.
Well, no, it doesn't have to be the same concentration as step one. This is not possible because of Le Chatelier's principle. What does Le Chatelier's principle say? That if you increase the product, we expect a shift left and establish a new equilibrium. So we increase the product, but was there any shift left? No, this cannot be equilibrium. This has to be your new initial. But we don't want to solve it this way because this is called the Le Chatelier's method. We already did the reset. We don't want to do that. And so then we'd have to set up another ice table below this to figure out the shift left. Your book doesn't do that sometimes. Your book just leaves it like this. The other way of thinking about this is, can the population grow back to its original? You know, in the absence of, hydronium is like a predator, right? If you have predator around, are the fields going to be full of antelope? No, because what's going to happen is the population is going to be lower. So this cannot be. It cannot go to the same population as before with no predator around. If this was 0 and 0, then there's open fields, right? And where deer and antelope can roam freely. But now we have this extra hydronium in here, and that's going to cause trouble, right? And so this is wrong. Your book does this. Be aware of that. This can't be, because we aren't going to generate the same population. This is Le Chatelier's type of effect. The population is going to be smaller, so I expect X to be smaller than 10 to the minus 7. Right? Not only that, you know, now that I have some hydronium here, you know, the product has to equal 10 to the minus 14, right? And so we expect X to be less than 1.0 times 10 to the minus 7 molar. It's got to be less than that. We already have hydronium present. We don't need as much. So this is going to be 1.0 times 10 to the minus 8 plus X molar, and then X molar. And then we could solve for KW. KW is 1.0 times 10 to the minus 14, which is equal to hydronium times the hydroxide. This is going to be 1.0 times 10 to the minus 8 plus X times X. I always try the simplifying assumption, just to see. If we try it, we got 1.0 times 10 to the minus 8 times X. X is equal to 1.0 times 10 to the minus 6. And it gives us a percent change of 10 to the minus 6 divided by 10 to the minus 8 times 10 squared. Which gives us a 10,000% change. Is that good? 10,000%? No, that's bad. So it's a fail. But it's all right because it barely took us any time to do that, so it failed. And so that means we have to use the quadratic, but that's not a big deal. We can use the quadratic to solve this. This one's easy to get in quadratic form. This is going to be x squared plus 1.0 times 10 to the minus 8x minus 1.0 times 10 to the minus 14 is equal to 0. So can somebody punch that in their calculator and see what x comes out to? 9.51. 9.51 times 10 to the negative 8. You see, we can't go all the way to 10 to the negative 7. It's going to be a lot smaller. And so here we got 1.0 times 10 to the negative 8 plus x, which is 9.51 times 10 to the negative 8. isn't this weird? Take a look at the numbers here. Consider this 10% of the hydronium, 90% of the hydronium. Actually, more than 90%. 10% of the hydronium in this solution came from, where did this come from? HCl. 10% of the hydronium in this solution came from HCl. 90% of the hydronium in this solution came from water. You see? And so most of the hydronium in this solution actually comes from water. We barely added any HCl. If somebody asked me to drink 10 to the minus 8 molar HCl, I wouldn't hesitate. I'd just drink it because you know what the pH of our tap water is? Our pH of the tap water is like 6. What's the pH of this? This is going to be, well, this is going to give me 10.51 times 10 to the minus 8 molar. But, you know, I have to make sure that the stepwise is justified. So how do I make sure that this method is okay? I need to check to see if this. Now I increase the concentration significantly, right? I increase the concentration significantly. Is that going to upset this step here? Because now I went from 1 to 10 molar. So 10-fold increase in the concentration. If I increase the concentration of the product 10-fold, what does Le Chatelier's principle say? It should shift it left. But is this one going to be perturbed by Le Chatelier's? No, because Ka is very large. So even though I did a 10-fold increase in the product concentration, I don't worry about it impacting step 1. And so step 2 does not perturb step 1, even with a huge increase.
So for all strong acids, it wouldn't ever disturb step 1 lower.
Yes.
So that would only
Occur for weak acids. If this were a weak acid, then I just screwed it up. If this were a weak acid, then Le Chatelier's principle says shift left. If it shifts left, then it screws up this concentration, which screws up this concentration. And so what I have to do is I'd have to do a Le Chatelier's fix of this.
So for weak bases, step 2 concentration will always be lower than step 1. It's for it to be right.
For it to be right, it has to be a lot lower.
A lot lower, right?
Yeah.
So it will never be higher for a weak.
It would be. It could be higher. It could be
So
higher.
that,
This is the next example. The next example is when it doesn't work, when stepwise fails. I'll show you when stepwise. Stepwise, the reason we want to start off with stepwise is because it's easy, right? But it doesn't always work. It's like in Chem 4, you did the pH calculations, you ignored Kw, but it doesn't always work, right? Well, that's okay. In Chem 4, you'll never get a problem like this, so you're safe. You won't get negative pHs. You won't get pHs greater than 14 because we want to keep you safe, right? It's like you don't introduce the a beginner on well, anyway. Going back to this, so we're okay. What is the pH that you calculate from this? 6.97. Give me one more digit. 8. Give me one more digit. We're allowed 3 sig figs. I'm going to carry one extra.
Another 8.
Another 8. A 3 after that?
6.783.
Oh, all right, we got this issue. Well, nonetheless, the pH is less than 7, like we'd expect. It's very dilute, so it's going to be close to water. So this is actually purer than our tap water here. Tap water has more acid in it. But the hydroxide, what is the hydroxide? The hydroxide is 9.51 times 10 to the minus 8 molar. And so this is what we're going to have. If I had a beaker, this is what we call the inventory of this. If I have a beaker that's labeled 1.0 times 10 to the minus 8 molar, what's inside of it? This is HCl. So it's labeled it. Well, what's inside this is I'm going to have 10.51 times 10 to the minus 8 molar hydronium. I'm going to have 9.51 times 10 to the minus 8 molar hydroxide. And I'm going to have 1.0 times 10 to the minus 8 molar chloride. And so this is what I expect to find in this, in addition to water. These are the species here. All right, so again, stepwise was a success. But in this case, I couldn't use a Chem 4 style. You know, in Chem 4, they forget about step 2. They assume step 2 is negligible. In this case, step 2 was hugely significant, so you'd never get this calculation in Chem 4. But you would get this calculation in Chem 1B. Now, the next example we're going to do is this. We're going to do this. We're going to do 1.0 times 10 to the minus 8 molar. Do we have HCN there? No. We're going to do this. 1.0 times 10 to the minus 8 molar HCN. And let me give you the Ka for HCN. The Ka values are located in our book and also in Appendix D. The Ka for this is a weak acid, so we have to pay attention to that. It's not a strong acid. And so we'll just get it from chapter 16. Chapter 16 is a smaller table of Kas. HCN is called hydrocyanic acid. Here. Here's the hydrolysis equation, and the Ka value for that is 6.2 times 10 to the minus 10. 6.2 times 10 to the minus 10. Oftentimes, you know, how many spaces does that take? A lot of spaces. So if we write it as a pKa, it takes up a lot less room. That would translate into pKa of 9.21. 9.21 only takes 4 spaces, 9.21, whereas this takes up 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 character spaces, which means you have to use a lot more paper to print this, which means this is much more compact. These two numbers are exactly the same. This is power function versus non-power function. So a lot of tables are in pKa rather than Ka. You know, and you have to interconvert. pKa is the negative log of the Ka, right? And the Ka is 10 to the minus pKa, just like the pHs and pOHs.
What does the P stand for?
Power function. Well, anyway, why don't you do this one next? The same exact setup. We're going to try it stepwise. We always tried stepwise first. Hopefully it works. That saves us a lot of headache and a lot of work. If it fails, then we have to do something called simultaneous, which is a heck of a lot more work. Talk about that.
What did you say was the formula? You said Ka was 10 to the something pKa.
Okay, it's always the power function is always the same. The power of anything is equal to the negative log of that thing. So if I'm looking at pKa, pKa is the negative log. Just take the negative log of 6.2 times 10 to the minus 10. And to convert it, if we want the Ka is the anti-log of the negative pKa. It's just a more compact way of writing things. It's like the Richter scale, you know, if you want to talk about the magnitude of earthquakes, you can use scientific notation. It's a hassle. You say 9.0 on the Richter scale means, you know, 10 to the 9th power earthquake versus an 8.0, well, 8 or 6.0, you know. So the difference between a 1 and a 6 or 0 and a 6 is like a million. You know? Six powers of 10. Same exact setup, except the first one, do you know what X is? Because a weak acid, if it's a strong acid, we know what X is, you know? But in step 1, we don't know what X is because it's a weak acid. Weak acids partially hydrolyzed. And so we have to do a little bit more work because in step 1, we actually have to do a calculation rather than doing it in our head. Well, we're out of time, unfortunately, so we'll continue this next time.